In this video you will learn how to use the formula for the loaded voltage divider, which we have looked at in the previous video, to calculate how to connect an LED, a light emitting diode, and a resistor to a stable 5-volt supply, which you generate using an appropriate setup of resistors in this very small network. And in order for this to work, the equation from the derivation of the voltage divider, of the loaded voltage divider, must be adapted, and an empirical value taken from practice must be assumed for the ratio of load current to divider current. This is the key for solving this problem of supplying a constant voltage for the load you want to connect. And I will also show you how you can easily determine the resistance of an LED by simply measuring the voltage in this branch of the voltage divider where the current flows, which is not going through the LED and through the resistor. This is a very easy means of directly measuring the resistance value of this nonlinear component LED. And finally, and as always, there's going to be a summary of the most important facts from this video at the end. And my name is Andreas from The Fearless Engineer, and here we go. If you have watched the previous video on the loaded voltage divider, you already know that it makes a difference if you have set up a voltage divider consisting out of 2 resistors to a voltage source, that it makes a difference if you leave it this way and use the standard equation for voltage division, or if you connect a third resistor in parallel to one of the resistors of the voltage divider. This is called the loaded voltage divider because you connect a load resistor, could be another external circuit which you want to power, to one of the resistors from the original voltage divider. And with the formula for the loaded voltage divider, the voltage supply of this circuit can be adapted to the load which you connect. Let's, for example, assume you want to safely operate an LED which is placed in series with another resistor. In another video we have used a 220 ohm resistor for this purpose. Let's say you wanted to supply this LED resistor combination with a stable voltage of 5 volt. You have a power source consisting out of 9 volt and you want to reduce it to 5 volt in order to safely operate this LED. You can use a voltage divider for this purpose, but as the LED and the resistor both have a resistance value, you are going to change the balance of the voltage divider setup. And this exercise, which we're going to conduct in this video here, is about how to properly dimension this voltage divider if a load is connected. And the approach we are going to choose here consists of 4 phases, so to speak, 4 steps. In the first one, we are going to look at the derivation of the loaded voltage divider, not because I think it needs repetition, but because based on the means of deriving the formula for the loaded voltage divider, there is an intermediate step from which we can very simply reshape the voltage divider equation to the purpose we are looking for. If we would simply look up the voltage divider equation from your set of from your collection of formulas, you most probably would choose a version which is very cumbersome to reshape. And if you take one of the intermediate equations on the road to deriving the final equation, that makes it much easier and quicker to solve such exercises, such tasks here. And secondly, fitting the formula to the target value is the next step based on this derivation here. And then thirdly, we will insert the numerical values and just simulate the circuit to look at whether we have computed correctly. And finally, as a bonus chapter, so to speak, we will calculate the resistance of the LED with a voltage divider. And as a bonus, so to speak, we will calculate the resistance value of a light emitting diode, which is a nonlinear component, using the equation for the loaded voltage divider. This is not measurable by using a multimeter, the resistance of this light emitting diode. Also, it's subject to change because the current voltage characteristic is nonlinear in its nature. But by using the equation which we derive in the course of this video, we will be able to compute the resistance value of the light emitting diode. What you can see here is the loaded voltage divider base circuit, which we discussed in the previous video on derivation of the loaded voltage divider. We have a power source, a voltage source here on the left. We have 2 resistors, R1 and R2, which are placed above each other, R1 and R2. And we have a third resistor now, which makes it a loaded voltage divider, which is placed in parallel to R2. And this resistor number 3 means that a certain fraction of the current flowing through R1 also flows is directed across R2, which also means that the current flowing through R1 is different from the current flowing through R2, and this renders the original base equation of the voltage divider useless in this case, because this one is based on the assumption that the current flow through both is identical, which is not the case here in this setup. Instead, we have to use another version, and one of the intermediate steps of deriving this voltage divider equation for the loaded variant is solving this junction equation here, which is the sum of the incoming and the outgoing currents based on Kirchhoff's first rule. And this equation, combined with Ohm's law and a few tricks here and there, yields this equation here, this intermediate equation. It's the sum of the currents flowing into and out of this junction here. And this one can be easily reshaped to U2, but as you can see, bringing all these values, combining all these values into a common denominator makes it very hard to solve for a particular resistor value here. Let's say you wanted to solve for R2 or R1 or R3, it doesn't matter. It's very cumbersome to isolate a certain resistor value based on this final form of the loaded voltage divider, which is what we will see on one of the next slides. It's much easier to base the derivation of a certain resistance value on this intermediate step, which is why we are repeating this derivation here to make it very easy to solve for, let's say, R1, R2, or R3 based on this equation here instead of this rather cumbersome one here. And the load resistance R3 is chosen in a manner that it's about 5 to 10 times larger than R2. This is a value taken from practice, and we have discussed the reasoning behind this in the previous video. But for this video here, for this exercise, we are setting R3 to 5 times the value of R2. So R3 is 5 times as large as R2 is. So that's the short recap of the derivation of the loaded voltage divider. And the task which you have to solve here is now that you want to include an LED which is placed in series to a resistor with a value of 220 ohm, and you want to place this across in parallel to a resistor R2. And the question is, how large must R1 and R2 be so that U2, the voltage drop across the second resistor here, is exactly 5 volts. So what you have given is the total voltage of the power source. What you also have given is the value of this resistor here directly in front of the LED. And for simplicity, you can assume in this first step that the LED resistor should be negligible in this case for the time being, so it's going to be 0. And the question now is how to choose R1 and R2 so that the voltage drop across the second resistor is 5 volts, which then supplies this LED which is placed in series to RV. Try to solve the task on your own. Try it now and press pause, because on the next slide I'm going to present you with my sample solution of this task here. Okay, now let's take a look at the first solution step here, in which we determine the value of R2. We have RV given, it's 220 ohms, and it follows from practical experience that the value of RV, or the value in the loaded branch, should be 5 to 10 times larger than in the current divider, voltage divider branch. And as stated on the task slide, on the previous slide, the difference is a factor of 5, which we are going to take here in this case. So since we know that RV is 220 ohms, we now multiply RV, or R3 as it's called here, with a factor of 0.2, which renders R2 to a value of 44 ohms. So R2 is 44 ohms in the setup, and now we have only one resistor missing in the setup. We are now looking for R1 because we have R2, we have RV, we have the total voltage drop, and we are now looking for the R1 which renders the voltage drop across R2 to a value of 5 volts. And now in the second step, what we want to do now is we want to compute the unknown resistance R1 based on the values which we have determined now for the rest of the voltage divider setup. And we can use the junction equation for this junction here, which we have looked at on the first slide, which introduced the loaded voltage divider at the beginning of this video. It's this equation here. And if we do not use the final form, which has this very complex denominator, but this form here instead, we can simply solve for the resistor we are looking for, which in this case is R1, R1, solve the equation like this, and then we have R1 being the difference between the source voltage and U2 multiplied with this expression here. And if we insert the values given in this circuit diagram here, we arrive at a value for R1 of roughly 29.33 ohms. This is the value we need to set R1 to so that U2 can be 5 volts. Okay, and here comes the answer. If we insert the LED into this branch here, we increase the resistance of this branch. We increase it because the LED is a nonlinear component whose resistance depends on the voltage drop across the LED terminals, and we do not fully know at this point in time how large the voltage drop across the LED will be if we insert it here, simply by looking at the circuit. But we know that it's not going to be zero, because for it to be almost zero, we would need a very, very large voltage drop. And this is not going to happen because this resistor here is going to limit the current to a maximum of 22.74 milliamps. This is the maximum current which will flow through the LED in case it had a 0 ohm resistor. It's going to have a resistor which is very much different from 0. It's going to be much higher, and this is why the current flowing through the LED is going to decrease significantly as soon as we enter it into this circuit here. And as you can see in the circuit here, by placing the LED in the same branch as the 220 ohm resistor, we lower the current from 22 milliamps to now 15 milliamps, just as predicted. And also the current across the resistor R2 increases to 5.138 volts. So we have changed the balance of the voltage divider by introducing this LED. And this enables us to now compute the resistance value of the LED for this operating point at least. We can base our computation again on the junction equation which we have used in the previous step. We can now solve for R3, which is the resistor of the load part. So the entire resistance inside this branch here, consisting of LED and resistor, this is called R3. We can solve the equation for R3. We can enter the values from the simulation, and then we arrive at the total resistance of this entire branch consisting of LED plus 220 ohm resistor is going to be at 341.7 ohms roughly. And if you deduct the 220 ohms value from of this resistor here from the overall value, then you arrive at a value of 121.7 ohms for the LED. So in this simulation, the LED has an ohmic resistance at this operating point of 121.7 ohms. And we have exploited our knowledge on the loaded voltage divider to arrive at the resistance value of the LED by measuring a few values and by reshaping this equation here. Now let's summarize the major takeaways from this video here. First is the junction rule, the junction equation from which we saw in the derivation of the loaded voltage divider provides us with a very simple starting point to quickly transform the equation to contain the desired quantity. We just need to decide for which resistance value, for example, we want to solve, be it R1, R2, or R3, and then reshape this equation. This is much easier than tackling this rather lengthy equation which is already solved for U2. This is, I think, an unnecessary waste of time. It's much easier to start from the junction equation, which we know from the derivation of the voltage divider. And second point here, in practice, the divider current should be approximately 5 to 10 times greater than the load current in order to find a good compromise between voltage stability on one hand for the load and also a bearable energy consumption in the divider branch, because we want to minimize the amount of current flowing through R2 simply because it heats up a resistor and wastes energy which we cannot use to power the load which we connected to the divider. And thirdly, third point, the resistance of the LED is of course variable, as we have seen before in the characteristic curve, and therefore we cannot directly include this into the calculation of the voltage divider simply by assuming it as a constant value, such as we did for example RV, which was 220 ohms. But we have to always consider the actual operating point, which makes it harder to take into account the properties of the LED in a viable manner. But we can use the resistance, we can use the voltage divider to to compute the resistance of the LED for a certain operating point by measuring the voltage drop across the lower resistor R2 and by reshaping the junction equation, which we have used so many times before now in this context. And this enables us to compute the resistance value of the LED in a very simple and straightforward manner. This is all for now. If you have any questions, drop them in the comment section down below. And as always, I wish you a nice day. See you next time here on The Fearless Engineer.